In this video, we're going to talk about the problems that you're going to encounter in section 2.7. 2.7 talks about linear inequalities and absolute value inequalities. These can be quite challenging problems, and I do have some handouts in D2L to help you out. You'll find it under course resources, Professor D's material just for you. And of course, you can use this video as well. So let's get to sharing our screens and let's see what these problems look like. What we're going to see now is we see in problem 1 that we have a linear equation in an inequality. An inequality means that you have one of the 4 inequality symbols instead of the equal sign. Less than or equal to, greater than or equal to. When we solve these, we approach it essentially the same as solving an equation, but there are a couple of rules that are a little bit different, really tricky rules. So let's take a look at problem number 1. Oops, I've got the wrong pen picked out. Let's go, oh, for fun, let's go with, we'll use black. On problem number 1, we're looking at 10x minus 4, less than equal to 2, not greater than. Now, this symbol that you see right here, that's the less than or equal to. Now, I confess, I was in college before I ever learned how to pronounce those symbols. I always prayed in class, please don't call on me, please don't call on me. Because in high school, I never knew which one was which. I just couldn't figure it out until someone finally explained it to me. You read the symbol from the left side to the right side. So if you're looking at the symbol and you encounter this narrow end first, that's less than. The little end, less than. If you encounter the wide end of the symbol first, like you would see in this one right here, that's greater than. So wide end of the symbol, greater than. Narrow end of the symbol, less than. Again, you read it from the left to the right, which is the typical order in reading mathematics. We read graphs from the left to the right, and we read symbols from the left to the right. Hopefully this helps you, and I sincerely hope you weren't in the boat I was, praying not to be called on. When we're looking at this problem, we want to isolate the x. In order to isolate x, we need to move the other terms to the other side. Now, there is something to be careful of. The one tricky rule with inequalities is if you multiply or divide by a negative number, you have to reverse the sense of the inequality. In other words, you reverse the symbol itself. Now, most of the time, not all of the time, but most of the time, 95% of the time, we can avoid this rule by always making sure that the variable x has a positive coefficient by adding or subtracting it to the side where it will have a positive coefficient. Now, adding and subtracting does not invoke that rule. It's only multiplication and division by a negative. So I'll show you the rule, but I'll also show you how to avoid the rule, because I generally think avoiding negatives is the better way to go. In this case, my variable term, 10x, already has a positive coefficient of 10. That means I'm going to leave it where it is, and I'm going to move the negative 4, which is next to it, by adding 4 to both sides of the inequality symbol. The inequality symbol is taken the place of the equals, and that's where it keeps things balanced. So I do the same thing to both sides of the inequality, and I get 10x is less than equal to 6. Now I'm going to have to divide both sides of the equation by the coefficient 10. But the coefficient 10 is a positive number, so it will not invoke that rule. Let's see what happens. When I take 10x and I divide by a positive 10, I don't reverse the symbol. I leave it turned the same direction it was originally. If I have that, then I end up with x on the left and less than equal to, and of course I can divide both of these by 2, and 2 over 2 is 1. So I'm allowed to do this, and this gives me 3 over 5. Now, how do I write this in terms of interval notation and on the number line? On the number line, remember that you have an arrow at each end, and you always put in 0 as sort of a here's home base kind of thing. And then 3/5. It can be anywhere you want it. If you label it, it is so. So if I call that 3/5, that's 3/5. Now, the less than or equal to, the or equal to means that I'm going to have a solid ball. So I make a circle and then I fill it in. If it didn't have the bar on the bottom of the symbol, I wouldn't make it a solid ball and make it an empty ball. Now the question is, which way do I go? Do I go to the left of the ball or to the right of the ball? It depends on where the variable is in relation to the symbol. It's not that it's on the left. Please, please, please delete that thought from your memory. This tends to be the way it's taught in high school, but not in college. In college, what we have you do is we always have you look at the variable in relation to the symbol. Which end of the symbol is the variable on? The variable is closest to the narrow end, which is the little end, which means go left. If the variable were on the right side, the larger side, we'd go right, since smaller numbers are to the left and larger numbers are to the right. And it looks like this. Now, how can we interpret this in terms of what's called interval notation? For interval notation, we want to write it using parentheses and square brackets. Now, when we write it with infinity or negative infinity, we always use a round parentheses with infinity and negative infinity because they're not numbers, they're directions. It's like saying go west and not telling how far to go west, just go that way. And that's essentially what infinity and negative infinity are. Go that way or go that way forever. But it's not a number. I'm not saying how far to go. I'm just saying that way. So in this particular problem, when we're looking at this up here, we start at the left side and we read it from the left to the right. The far left over here is negative infinity, and it includes that because of the arrow. So we start at negative infinity, comma, and we go until it stops at 3/5. Negative infinity is on the left and 3/5 is on the right. Be very careful about this. This is a very, very tricky thing. And a lot of students will get them written backwards. Again, you write them in order, left to right. Now, should we use a round parentheses or a square bracket? Our options are round parentheses, round with a square, square with a round, square with a square. So which one is it? Well, is it a solid ball or not? If it's a solid ball, it means it can be 3/5. So it actually can use the number 3/5. I like to think of it as a clamp that's clamping down on 3/5 and holding it tight. And that tells me to use a square bracket, which is tighter. The round to me looks more like an empty hole not hanging on tight, which means it's not actually used. That's the way I remember it. This is our interval notation, negative infinity to 3/5. Now, I'm not entirely sure how WebWork is going to interpret infinity, but I think the letters I and F will do it. Let's see. We start with a round parentheses for all infinity and negative infinity, and we put negative INF, comma, 3 divided by 5, and then a square bracket, which is on the keyboard above and to the left of the enter symbol. Let's see if it will take this. Yes, it does. So we can use INF to interpret infinity. Notice that the answer preview right here matches what I have on my page right here. You want to ensure that the answer preview is what you thought it would interpret it as. It may be, if this doesn't look like this, that you put a symbol in the wrong place or omitted a symbol by accident. Always check the preview if you don't get the right answer. Let's take a look now at the next problem. In problem number 2, we have another problem. This time, I'm going to deliberately do it the way that I told you I don't do it so that you can see what happens. Remember to put a horizontal bar between your homework problems and to number the problems and copy the problem. This is to protect you on tests in case you copy the problem wrong. Then I know what you're starting with. If I know the problem you copied is wrong, I'm not going to count off for that. If you work that problem correctly and you follow the steps that you were supposed to be doing on a different problem, I'm going to give you full credit. But if you don't copy the problem, then I don't know where the error is, and I can't give you as much partial credit. Now we're looking at this problem right here, 3x plus 2 greater than or equal to 6x minus 9. It's greater than or equal to because from the left to the right, we encounter the bigger end first. This time, I'm going to move the 6x to the left, and that will make it negative, and that will invoke that special rule. Then I'll rework the problem, showing you a different way of doing it. I'm going to move the 6x to the left by subtracting 6x. That means the variables will end up on the left side, so then I'll move the constants to the right side. Again, I'm trying to isolate the x terms. This is much like solving a linear equation, basically the same steps. Start by isolating the x terms and then isolate the x variable. This gives me negative 3x greater than equal to negative 11. The next thing I need to do is isolate x. To isolate x, I need to divide by negative 3. But this invokes that weird rule for inequalities. If you multiply by a negative or you divide by a negative, you have to take the symbol and turn it around. Just the symbol, not the sides. This means that when I divide both sides by a negative 3, I'm going to have to take the symbol, which was greater than or equal to, and turn it around in order to have less than or equal to. This is called reversing the symbol. I don't like this rule. It's hard to remember and it's tricky. And plus it has negatives involved. Generally not a good idea to do. So I'll show you a better way of approaching the same problem. What happens now is we get x on the left and it's less than or equal to a positive 11/3 on the right. Let's go ahead and interpret this. If we have this, then on the number line, we have arrows on both ends, 0 for a placeholder, just slap a spot to the right and call it 11/3. Now, do we have or equal to? We do. In that case, we're going to make a ball at 11/3 and we're going to fill it in solid. Then we look to see which side the variable is on. The variable is on the narrow end, and the narrow end next to the variable means go left. So we go to the left. Then we interpret the picture in order from left to right and write it in interval notation. On the far left of the picture is negative infinity, comma, and on the right of the picture is 11/3. The ball is solid and we have or equal to, which means we're wanting to use 11/3. So we clamp down hard on it and we make it a square bracket. Now let's look at solving this problem in a different way. We're going to start over at the beginning of the problem, and I'm going to avoid having a negative variable term. Now I have 3x plus 2, starting over, greater than equal to 6x minus 9. How can I avoid dividing by a negative or multiplying by a negative? Always move the smaller variable term. Look at the numbers. If one's positive and one's negative, always move the negative one. If they're the same sign, always move the one that's further to the left on the number line. In this case, 3x is smaller than 6x, so I'm going to move the 3x instead of the 6x. That's going to put the variables on the right side of the inequality, which means the negative 9 should go to the left. I'm going to add 9 to both sides. I've kept it balanced across the inequality, so I haven't changed the solution set. But I have changed the way it looks. Now it looks like 11 greater than equal to 3x. Don't worry, it's okay to have a variable on the right. I don't know why they always avoid this in high school. It's not a big deal. We don't care. Now, what's the next thing? We're going to take the 3 and we're going to divide by the 3. However, the 3 we're dividing by is a positive 3. When you divide by a positive or multiply by a positive, that rule does not come into play. We do not reverse the symbol. That means that my final solution is 11/3 greater than equal to x. Now, how do I interpret this? Let's draw our number line again. Put 0 for a placeholder, a reference point. 11/3 is to the right because it's positive. And then we've got or equal to on the bottom. So we have a solid ball. And now we need to decide which way to go. Again, look at the variable and look at the symbol. The variable is on the narrow end of the symbol, which is go left. We got exactly the same result we got the first time, but without having to reverse the symbol. Now, if it truly bugs you to have the variable on the right, you can turn the equation around. However, turning the inequality around means you have to turn everything around, but you have to maintain which side of the symbol the x is on. The x is on the little end. So to turn it around and have x on the left and 11/3 on the right, you have to reverse the symbol so that the narrow end is still pointing towards the x and the wide end is still pointing towards the 11/3. That maintains what we call the sense of the inequality. In this way, you can avoid having to invoke the rule of multiplying or dividing by a negative. Now, I said there are some occasions where you can't, and that's when we have what are called continued inequalities. In continued inequalities, it is sometimes impossible to avoid. Let's now take a look at another problem, although I suppose we should put our answer in first. Again, from the picture of the inequality on the number line, we have negative infinity at the far left, then 11/3, solid ball, clamped down hard. So this gives us negative infinity, comma, 11 divided by 3, clamped down hard. Oops, I've got my symbol going the wrong way. Let's see what it does just for fun. It says I have an extra closed parentheses. Looking back at what I entered, I can then see that I've got too many closed parentheses and not an open one. Now we've got it correct. Let's take a look at this problem right here. This problem is going to be a little bit more difficult because of the fractions, but I'll show you a way to get around those fractions. Getting around fractions is always better than working with them, at least in my opinion. Okay, let's take a look at number 3. In number 3, we have negative 1/2 x less than equal to. Why are they all less than equal to or greater than equal to? Where are some of my strict inequalities? Negative 9/4 plus 7/8 x. Okay, the first thing I'm going to do is note that I have fractions in this. And then I'm going to note the denominators that I have. My denominators are 2, 4, and 8. Two is 2 times 1, 4 is 2 times 2, and 8 is 2 times 2 times 2. In other words, they all need at least one 2, but 4 needs another 2, and 8 needs yet another 2. In other words, the lowest common multiple of those numbers is 8. Let's multiply every term on both sides by 8 to clear it of the fractions. I like to put the left side of the inequality in parentheses and multiply by 8 over 1, and the right side in parentheses and multiply by 8 over 1. If I have more than one term, I'm going to draw arrows to be sure that I distribute it over both terms. Another way of doing it is simply to write it on each individual term. Now, 8 divided by 2 gives me 4. So this becomes negative 4x less than equal to 8 divided by 4 is 2, and 2 times negative 9 is negative 18. 8 divided by 8 is 1, so I'm left with just 7x. Why didn't I reverse the symbol? Well, the 8 I multiplied by was a positive 8. Yes, a couple of the terms had negatives, but that's because the negative was on the term, not on the number I was multiplying by. The number I multiplied by was a positive 8, so it does not invoke the rule. Now I have this equation right here. Looking at the numbers, I have negative 4x and 7x. A negative is always smaller or to the left of a positive number on the number line, so I'm going to move the negative 4x by adding 4x to both sides. That means the variables will end up on the right side, so I need to move the negative 18 to the left side by adding 18 to both sides of the inequality. That puts 18 on the left side of the symbol and 11x on the right side of the symbol. Notice the symbol does not turn around because this was addition subtraction. The only thing that causes it to reverse is multiplication or division by a negative. Now I'm going to divide both sides by 11. Since the 11 is a positive 11, I do not reverse the symbol. Note that what I'm trying to accomplish here is to isolate x. And what I accomplished here was isolate the x term. This gives me 18 over 11 less than equal to x. Now I'm going to draw my number line, arrows on each end, 0 is a reference point, 18/11 is positive, so it's to the right of 0. It is or equal to, so I have a solid ball there. Now I have to decide which way to go. Look at the variable and see which side of the symbol it's on. It's closest to the wide end, which is go right where the bigger numbers are. Now let's interpret this by reading it from the left to the right side. It starts on the left with the solid ball. So we put a square bracket, 18 over 11, and then it goes to the right where positive infinity is found. With infinity and negative infinity, you always use round parentheses because they're not numbers. Now let's put our answers in and see how we did. Square bracket on the left. Well, I can't see my numbers again. 18 divided by 11, comma, infinity. Round parentheses. Where's my round parentheses? Perfect. Let's take a look at this problem here. This problem just gets a little bit more complicated. We'll take a look at this one and then we'll probably move on to our more complicated type of problem, a different type. In number 4, we have negative 4 times x minus 3 plus 6 greater than 8x minus 3 minus 3x. Well, the first thing to note is I have two terms on the right side of the equation that are like terms. I could go ahead and combine them directly. 8x minus 3x is 5x. There's no need to add or subtract on both sides of the equation. They're already on the same side. On the left side, in order to isolate the x terms, I'm going to have to get rid of the parentheses that you see here. So I'm going to distribute the negative 4 over both of the terms on the inside. That gives me a negative 4x plus 12 plus 6. The plus 12 and plus 6 are both on the left, so I can combine them to get negative 4x plus 18 greater than 5x minus 3. Now we decide where the variables go. If we always move the smaller variable term to isolate the variable terms, we'll never have to invoke that weird rule about multiplication and division of a negative reversing the symbol. That means that when I move the negative 4x, I get a plus 4x on both sides of the inequality. The variables then are moving to the right, so I'll move the constants to the left by adding 3 to both sides. This gives me 21 greater than 9x. Now I can divide both sides by 9, which is a positive 9, and will not invoke that rule. Now 21 and 9 are both divisible by 3, so we should reduce it at least a little bit. I absolutely hate it when students make me do their arithmetic. So if you can reduce it, reduce it. It's not my job to do your arithmetic. You've got to do your own. This gives me divided by 3 over divided by 3, which turns out to be 7 over 3, greater than x. Now we're going to draw the number line, arrows on each end, 0 for a reference. 7/3 is positive, so it's to the right of 0. We do not have or equal to, so we'll make an empty ball at 7/3. Which way do we go? Well, it depends on which side of the symbol the variable's on. The variable is here on the narrow end of the symbol, which means go to the littler numbers to the left. Now we read this representation from the left to the right to convert it to interval form. On the far left, we have negative infinity, comma, and on the far right, we have 7/3. However, we do not want to use 7/3. This was not or equal to, and this is an empty circle, and half of an empty circle is a round parentheses. Go ahead and put this in and let's check how we did. We're on a roll. Okay, let's see what the next problem looks like. The next problem is slightly different. Well, it's a lot different. How is it different? It has an inequality, greater than. Remember, read left to right. Right in first is greater than. But it also has an absolute value. Now, these can be more difficult to interpret. And I think that absolute value inequalities are among the more difficult ones that we see, which is why I have a handwritten handout for you to follow if you need more guidance. Let's take a look at setting up problem 5 and interpret it in terms of the distance from 0 on the number line. Remember, that's what absolute value means. So we're going to still isolate the absolute value, and we're still going to replace it with the idea of the distance from 0 on the number line. Our problem here is the absolute value of 10x minus 3, the quantity, greater than 15. What does this mean? First, we isolate the absolute value. And then we interpret it as the distance of 10x minus 3 from 0 on the number line is greater than 15. Well, what does that mean? We've interpreted in terms of words, but what does it mean in terms of a picture on the number line? Let's put the number line up and let's take a look at what it looks like. Put 0 in for a reference. Now, if the distance is greater than 15, how could I be 15 steps away from 0? Well, I could be at 2 different numbers. I could be at positive 15 here or at negative 15 here. But it said the distance is greater. So how can I be further away than 15? Well, if I can't be 15, I've got to have an empty circle at 15 or an empty circle at negative 15 because it doesn't have an or equal to in the problem right here. Now, how can I be further away from 0 on the number line? Well, I could get further away by going to the right from 15 or by going to the left from negative 15. Oh, well, that's where 10x minus 3 is. 10x minus 3 has to be in one of these ranges. Let's interpret this picture now in terms of symbols so that we can solve the rest of the problem. First, we isolate the inequality. Then we think of it in words as the distance of that part inside the absolute value from 0 on the number line. Then we draw a picture which represents that distance. And then finally, we interpret the distances on the number line in terms of symbols. What does this mean? 10x minus 3 is to the left of negative 15. That's what this represents. This is where 10x minus 3 is, and it's on the left side of negative 15, which somehow didn't get drawn completely. Or we have another possibility. The other possibility is called 10x minus 3 being to the right of 15. Now, how can we say that it's to the right? Remember, to the left means being on the little end. So being to the right means being on the wide end. And that means we put the wide end of the symbol and then 15. What is this actually interpreted as? I call these splits. You can have a continued inequality like a dumbbell shape, or you can have a split. When you have an absolute value greater than a number, you end up with a split situation where what's inside the isolated absolute value is less than the negative or greater than the positive. That's one way to interpret it. I like going through the symbols and the picture because the picture really makes it real for me and connects the ideas with the concepts. Now I solve these two problems separately. Add 3 to both sides of this inequality, and I get 10x is less than negative 12. Then I can divide both sides of the inequality by a positive 10, which does not invoke that division rule, reverse the symbol. And then I reduce this by dividing both of them by 2. This finally gives me the result that x is less than a negative 6 over 5 as one possibility. Let's take a look at the other possibility. Over here, I again add 3 to both sides of the inequality to get 10x greater than 18. Then I divide both sides of the inequality by a positive 10, which does not invoke the rule to reverse the symbol because the 10 that I'm dividing by is positive. Oops. This is 18 divided by 10. I got a little carried away when I was talking. Then I can divide both the numerator and the denominator by 2 to reduce it. And this gives me x greater than 9 over 5. Let's interpret this. Again, remember that the original gave us this sort of split apart situation. And we should expect that down here, it's probably still split apart. This time we have the arrows, 0 for a placeholder, and 2 numbers on the number line, negative 6/5 and 9/5. Negative 6/5 is negative, so it's to the left. And again, I'm not going to take off if yours aren't exactly the right distance. I'm looking for a general picture. 9/5 should be a little bit further out, and it's to the right. Now, how could x be less than negative 6/5 or greater than 9/5? And the answer is it has to be an or. It can't be in both places at once. The places aren't connected. So in this case, it could be to the left on the little end of the symbol. So I would draw an empty ball at negative 6/5 and go to the left. Or it's on the wide end, so we go to the right of 9/5, empty ball, and to the right. Now let's interpret this and write this in interval notation. Far left is negative infinity. Then it goes until it stops at negative 6/5. That's an empty circle, so we put a round parentheses. Then we use what's called the union symbol, which looks like an uppercase letter U, but without the tail on the end. Union means plus another little bit, or this other part as well. Then it picks up at 9/5. Again, we're reading left to right. So the next thing we hit is 9/5. It's an empty circle, so we use round parentheses. And then it goes to the far right, which is where infinity is found. Let's try entering this into WebWork and see how we do it. I'm thinking we should use an uppercase U. So we have parentheses, negative infinity, comma, -6/5, close parentheses, and let's try a union and see what it does. And then we have 9/5, comma, infinity. And always with infinity and negative infinity, we use round parentheses. Let's see when we do check answer if it interpreted our answer in the same way we meant for it to be interpreted. And it did. And it also took the uppercase letter U as the union symbol that you see here. These are more difficult problems, so I want to work at least another one or two of these. Let's look at number 6. There are various types of these. There are splits and there are dumbbells. This one's also going to be a split. Let's take a look and see how I knew it was going to end up with a split situation. The reason I know it's going to be a split situation is because when I isolate the absolute value, it's going to be greater than a number. That results in a split. But first, I have to isolate the absolute value before I can interpret it in terms of distance. So I'm going to move the -1, or move the 1 by subtracting 1. That gives me the absolute value of x minus 1 greater than 9. Now, how do I interpret that? This is the distance of x minus 1 from 0 on the number line is greater than 9. In other words, I have to be more than 9 steps away. Let's see what that looks like on the number line. If I'm 9 steps away, I could be at 9 or I could be at -9. But to be more than that means that I have to go further from 0 to the right of 9 and further from -9 to the left to get away from 0. Now this is where x minus 1 is sitting. X minus 1 is on the left side of -9. X minus 1 is on the narrow end of -9. Or, and it has to be an or because it can't be in both places at once since they're not connected. Or x minus 1 is on the right side, wide end of the symbol to the x minus 1 of +9. And then we solve them separately. The interior of the absolute value is less than the negative or greater than the positive of what was left on the right after we isolated. Note that when we introduce the negative, that the symbol does get turned around, which makes sense in light of the rule. Now we can say that we get x equal, or rather x less than, oops, just not a good symbol, start over, x less than -8, or x greater than 10. This is a split situation, and when we're looking at the picture on the number line, we have -8 here and 10 up here. It doesn't include -8 because it's not or equal to, and the variable is on the narrow end, so we go left. This is where x is. On the other solution part, we have x on the wide end, but not equal to, so empty symbol, go to the right of 10. Again, that's where x is. If x is in one of these two places, x minus 1 will be in one of these two places. Now we interpret the picture in terms of interval notation. We go for the far left and we work our way to the far right. On the far left, we have negative infinity, comma, stop at -8, but don't include it. So use round parentheses. Union, pick up again at 10, and keep moving to the far right to infinity. Use an uppercase U for the union symbol. Union is set notation for and also this part too. I think I've got it entered correctly. Let's take a look at the possible solution. This does look like what I entered here, and it is correct. Let's take a look at problem number 7. Problem number 7 is a special case, and it's always worth looking at the special cases. In this case, we have the absolute value of x plus 4 greater than -1. I need to isolate the absolute value first, and I have isolated the absolute value. It's already on the left by itself, but let's interpret in words what this means. The distance of x plus 4 from 0 on the number line is more than or greater than -1. Okay, that something about that doesn't sound right. The distance is more than negative. Well, all distances are more than -1. Distances are always strictly positive. So what does that mean? Well, if the distance is more than -1, then it doesn't matter what I put for x, it's always going to be true. This is an example of one where we end up with an identity, which basically says that this is always true. This is a non-negative greater than a negative, which is always true. If it's always true, then everything is the solution. And if everything is the solution, then the solution includes all the numbers from -infinity to +infinity. Now, if there's a special case where it's greater than a negative, there must be a special case where it's less than a negative. Let's look at the same problem, but let's let it be less than -1 and see what that would mean. This would be interpreted as the distance of x plus 4 from 0 on the number line is less than -1. Ooh. Yeah, it just doesn't sound good when you replace the absolute value with the distance. It automatically kicks up your subconscious saying, wait a minute, something's not right. The distance is less than -1. That's not possible. Absolute values are non-negative. And since they're either 0 or positive, they can't be less than a negative. There's nothing I can put in that's going to make this one true. There's no solution to this problem. We also call this the empty set, which is sometimes written with a 0 with a long diagonal slash through it to represent what's called the empty set. In other words, no solution. The empty set can also be shown with a pair of curved braces with nothing on the inside. My guess is, though, if this pops up in WebWork, it will ask you to type in none or no solution. The next problem is much like one we've done before, so we're going to leave this one for you to try at home. Let's take a look now at this problem right here. Actually, I want to go back and I want to solve a different type that just didn't come up in the list, but may come up on your homework. Let me create a problem for you now. This time we have an absolute value less than or equal to a number. We have not seen one with the absolute value less than or less than equal to a number yet. These lead to what's called a continued inequality, which is a three-part inequality, which is going to be the next type we're going to see in problem number 9. Let's interpret what this means. First, we isolate the absolute value, which ours already is isolated. But remember, that has to be accomplished first. Then you interpret it as a distance. The distance of x plus 3 from 0 on the number line is less than or equal to 5. What does that mean? Well, let's draw it in picture form. We've got 0, and I know the distance has to be less than or equal to 5. If it were equal to 5, how far away could I be? Well, I could be 5 steps to the right, which would be at 5, or I could be 5 steps to the left at -5. That would put the distance from 0 to be exactly 5. Now, if the distance is less than that or equal to that, if it's equal, it means it's a solid ball, so I fill it in. If it's less than that, it means it's closer to 0, which must mean that it's coming in this part here between the two. I call this a dumbbell shape. This leads to a continued inequality. If I interpret this in terms of where x plus 3 is, then I write a 3-part inequality, starting at the left and moving to the right. -5 is on the left. X plus 3 is in the middle, and 5 is on the right. Now let's put the symbols in to represent where x plus 3 is in relation to the two endpoints. X plus 3 is on the right side of -5, so we should have the wide end of the symbol towards the x plus 3. However, it's on the left side of 5, so we should have the narrow end of the symbol here. That means that x plus 3 is between -5 and 5. This becomes a 3-part inequality, which I can solve by isolating the variable term in the center. Now, this only works if the variable term is in the center. If the variable term is in the center, I can solve it in the 3 parts. What it really means is I've got an and equation. This is -5 is less than equal to x plus 3, and not or, x plus 3 is less than equal to 5. If I had the variable showing up in more than one location, not just the center, but on one of the endpoints, then I would have to split it into the 2 equations and solve them separately. Because this is written, however, with the variable only in the center, I can solve it directly by leaving it in the center and isolating the variable in the center. In order to do that, I have to move the 3 by subtracting the 3. I'm trying to isolate the x term. Now, if I subtract 3 and I've got 3 parts, it's kind of hard to show with only 2 hands, but I have 3 parts. I have to do the same thing to all 3 parts to keep the solution the same. That means I subtract 3 from the left and I subtract 3 from the right. Since I'm doing the same thing to all three parts, this leads to -8 less than equal to x less than equal to 2. Now, how do I interpret this solution? Again, I'm going to put this on the number line. Here's 0 as a reference point. 2 is about here, and -8 is about here. They both have or equal to, so I'll make them both solid balls. X is on the right end of -8, but it's on the left side of the 2, which means that it's between those two numbers. This is a dumbbell shape, like a dumbbell for lifting weights. Then we interpret this and write it in interval notation going from left to right. This is a square bracket because we include the -8, and then we move to the right to 2 where it stops. It's a square bracket because we include the 2. And this would be the interval notation form. Let's take a look now at this continued inequality that we have here in problem 9. It's a skill builder problem to get you to the steps to where you can solve an inequality or with an absolute value less than a number. We have in problem number 9, -5 less than 3x plus 5 less than equal to 12. Notice that my symbols aren't both the same form. This one is strict inequality and this one is or equal to. That will mean one of the balls will be solid and one will be open. I only have the variable term in one location, which is here in the center, so I can work it as a continued inequality. This means that 3x plus 5 is between -5 and 12, and -5 is to the left of 12. I'm going to subtract 5 to isolate the x term. This gives me -10 on the far left less than 3x less than equal to 7. The next thing I need to do is isolate the x variable. So I need to divide all three terms by 3. When I do this, note that if this had been a negative number, I would not have been able to avoid that rule where we have division by a negative reversing the symbols. In this case, though, the 3x is positive, so I'm dividing by a +3, which will not reverse the symbols, even though this has a negative on the 10. The number I'm dividing all three parts by is positive, so I do not reverse the symbols. This leads to -10 over 3, strictly less than x, less than equal to 7 over 3. On the number line, we can draw a picture, and this would look like the following. 0 for a placeholder, -10/3 down here, 7/3 not quite so far out. Then on the -10/3, we have an empty circle because it doesn't have the or equal to. On the 7/3, we have a closed circle, a solid ball, because we do have or equal to. X is on the right side of -10/3 and on the left side of 7/3. That gives us a continued inequality or a dumbbell shape. Now we interpret and go from the left to the right. This is going to give us a round parentheses, an open one on the far left at -10 over 3. Then continuing to the right, we stop at 7/3. We use a square bracket because it's solid. And so our solution would be -10/3, 7/3 closed. We say -10/3 is open and 7/3 is closed. Now let's take a look at this problem. On this problem, note that you have an absolute value less than a negative. We've talked about this, right? If I have an absolute value, this is a not negative number, less than a negative number. The distance, it's already isolated. So the distance of 3x minus 3 from 0 on the number line is less than a negative 3. No distance is less than negative 3. So there's no answer to this solution. None. In the next problem, you have a series of problems which will give you either splits or dumbbell shapes. Remember that when the absolute value is less than equal to or less than a number, then it will be a dumbbell shape. When it is greater than or equal to a number, it will be a split shape. What about this one right here? Let's take a look at number 4. This says the distance of x minus 4 from 0 on the number line is less than infinity. Well, infinity is larger than any finite number, and a distance is a finite number. So it seems to me like anything would work for that. So I think for that one, it must be answer E. This has to be from negative infinity to infinity. I'll leave you to solve the other ones, but that's how you would solve that particular one. The last one is an absolute value less than 30, which is going to give you that dumbbell shape. I'm going to leave you to solve that one on your own since I've already done an example or two of that. And I hope that this helps you in solving the problems out of section 2.7. This will end the material for exam 1. In the next video, we'll be starting the material for exam 2, which starts in section 3.1.